Okay, we're going to continue on in the chapter of rotation. And I think the last thing I had posted, okay, was the fan. Okay. So right after that, I tried to make the connection between the old stuff in chapter 2, okay, linear motion of a car going down the road, and rotational motion. Okay, so remember from chapter 2. Okay, remember the first week we had a car to light. Okay, remember that? And we said that after that second week we would never talk about that car again. Okay, remember that? Okay, so I formally deny that we ever said that. So here's that car. So this is what we did. So the car's at rest, okay, in that problem. Car goes down the road. And equation number 1 allowed us to find how fast the car was going at a certain time. Equation number 2 allowed us to find where the car is at a certain time. And equation number 3 allowed us to find how fast the car is going after it's gone a certain distance. Okay, so we tried to make the connection between position, velocity, and acceleration from chapter 2 and their rotational counterparts. When I take the road, there's a road, and I bend it in a circle. So instead of the car going down the road, and after 10 minutes you don't see the car anymore, the car is going around in a circle. So position gets mapped to its rotational counterpart, angular position. Okay, so when the car moves, okay, you have an angular position. When angular position moves, you have an angular displacement. And as the car goes around the circle, you have an angular velocity. So velocity gets mapped to its rotational counterpart, angular velocity. And if the spin rate changes, just like the car can speed up, so if the car has an acceleration, okay, in a straight line, now I take the straight line, I bend around the circle, then A, acceleration, gets mapped to its rotational counterpart, alpha, which is the angular acceleration. Okay, so we're going to have our equations 1, 2, and 3 again, but now they're going to be written in terms of the rotational variables. So this is what we're going to see. All the x's get replaced with thetas, all the v's get replaced with omegas, and all the a's get replaced with alphas. And that's why on the next test, or I should say on the exam where this chapter is on the exam, that these three equations, 1, 2, and 3, are on the equation sheet. And I don't give you the new ones we're going to look at because all you have to do is just take the old ones and replace x with theta, v with omega, and a with alpha. Okay, so let's see why that is. All right, so here's my car. Let's say it's going around a circular track. So again, this could be a car or could be a bike wheel. Okay, but it's easier to think about here's a car. Okay, so it has some angular displacement. It has a rotation rate, so it's going around a circle, so many revolutions per second, right? It has to be in radians per second. And if it's speeding up as it goes around the circle, it'll have an angular acceleration alpha. So remember from chapter 2, okay, this was the definition of acceleration, change in velocity with respect to time. So we're changing velocity like that. We did this the first week, okay? Multiply both sides by t. Okay, put a t there, put a t there. Okay, and we got that. And then I just solved this for v final, and that was equation number 1. Okay, now I'm going to do the perfect mapping. So acceleration is now compared to its rotational counterpart, angular acceleration. Okay, so just like a is change in velocity with respect to time, angular acceleration is change in angular velocity with respect to time. So I wrote delta omega, final minus initial, multiplied both sides of this thing, okay, by t. So you multiply by t on that side, multiply t on that side, and I get that. Okay, and then solve this for omega final. So this looks just like equation number 1, where v final is replaced with its rotational counterpart, omega final. Initial velocity is replaced with its rotational counterpart, initial angular velocity, and a is replaced with its rotational counterpart, angular acceleration. So that's what I mentioned before, that when we have the exam in this chapter, this equation's on the equation sheet, okay? That one's not, okay? Why or why not? Because I want you to realize it's the exact same idea, okay? Car goes down a straight line, and now I bent the straight line in a circle. So once you know equation number 1 for v, you know equation number 1 for omega. It has the exact same form. Just replace velocity with angular velocity and so on. Okay, so here's an example. All right, so here's the car, It's initially at rest, and it's going to put, the person in the car is going to put their foot on the gas, and they're going to accelerate around the circle. So that's their angular acceleration. And I want to find what's their rotation rate, what's their angular velocity at 3 seconds. Okay, so this is the circular version of just saying I have a car, okay, at rest. They put their foot on the gas, the acceleration would be 2, and what's the final velocity at t equals 3 seconds? Okay, so it's just like that, but it's in a circle. Okay, I'm not finding velocity v, I'm finding the angular speed. Okay, how many revolutions per minute? Okay, but it has to be in radians per minute or radians per second. Okay, so I want to find the final velocity at a certain time. That's equation number 1. Equation number 1, initial angular speed or angular velocity is 0. There's my angular acceleration, there's my time. Okay, one of the s's cancel. Okay, so that's its rotation rate. All right, so it's the exact same as we did, car going down the road, okay, but now it's going in a circle. Okay, then in chapter 2, we had this that told you where the car was at a certain time down the road. All right, so now we have the car going in a circle. So we can use, and the book does this, you use the exact same algebra we did in week 1 or 2 to derive equation number 2, use the exact same way to get that expression. Okay, so position x gets replaced with its rotational counterpart, angular position. Initial velocity gets replaced with its rotational counterpart, angular velocity, and acceleration gets mapped to angular acceleration. Okay, so that's what I mean by this equation's on the equation sheet, this one's not. Because as long as you have that one, you just replace x with theta, v's with omega, and a's with alpha. I mean, it really is that simple. I want you to see that pattern. Okay, so let's say we had the same problem. The angular acceleration was 2 radians per second squared. Okay, remember this thing's spinning faster and faster. What's the angular displacement of the car? That's the car, or it could just be a wheel. Okay, this whole big thing, okay, could be a wheel. What's the angular displacement of the wheel after 3 seconds? Okay, so remember, angular displacement is my delta theta. All right, so what I'm asking here is, okay, not how far the car went down the road. Okay, we're not asking for an x, how far it is. We want to know how many times did it go around? How many revolutions has it rotated? Okay, but we want that answered in radians because angular displacement is in radians. So looking for delta theta. Okay, so again, this would be the same thing as asking where is the car, x final equals what after 3 seconds. Okay, so we would use equation number 2. This is equation number 2. So here I wrote equation number 2, this is equation number 2, and I brought theta initial over, right? So theta final minus theta initial is delta theta. Okay, so I bring this thing over, then I can write this as delta theta. Okay, so this is equation number 2. Okay, so my initial, let's see. So this is the same car where initial angular speed was 0. So initial angular speed, angular velocity is 0. And I have 1/2 alpha t squared. Okay, so the s's cancel, and I wind up with 9 radians. Okay, so that's my angular displacement. All right, so it kind of makes more sense too to get an idea of, well, what is 9 radians? What does that mean? Well, we can also ask, how many times did the car go around the track? How many revolutions is this? Well, I wrote my 9 radians, and then in 2 pi radians, I have 1 revolution. So the radians cancel out, and that says the car went around 1.43 revolutions. So the car started here, okay, went around once, and then it got to that point there. So the total angle looks like that. You start here, goes like that. So that's my angular displacement. Okay, so again, instead of the car going down the road and you don't see the car anymore, it's gone so far down the road, this car just keeps going around the circle. Okay, now what's the car's angular speed after 1 revolution? That's a 1 revolution. Okay, that's the same as asking how fast is the car going at a certain place. Okay, so I want the final angular speed, okay, after it's gone around once. All right, so the angular displacement, okay, is 1 revolution, but that's not in the correct units. It really has to be in units of radians. So 1 revolution, Okay, I took revolution, and I said 1 revolution, I have 2 pi radians. So the revolutions cancel. So once around is 2 pi radians. Okay, so again, so I want to find what's the final angular velocity after it's gone a certain angular displacement. Okay, so that's like equation number 3. Okay, what's the velocity after it's gone a certain distance? Here I'm asking what's the angular velocity after it's turned a certain angular displacement. So I write down number 3. Okay, initial angular speed, it's from our car, from 2 pages up is 0. Okay, there's my same alpha I'm using, and now my delta theta, I don't put in 1 revolution. Okay, you have to put it in radians. Okay, so remember, this is squared here, take square root of both sides, all right, and that gives me my final angular speed. All right, so it's similar to what we did for a car going in a straight line. Exact same equations of motion. Whoops. Okay, number 1, 2, and 3. But the x's are now thetas, v's are now omegas, and the a's are now alphas. Okay, so continuing on, here's a problem where I have a CD spinning, okay, at 300 revolutions per minute, and it stops in 2 seconds. And I'm asked to find the angular acceleration of the disk. Okay, so again, I showed that this is analogous to we did in chapter 2. Okay, so the numbers don't make sense for the car, but imagine I have a car moving with a velocity, initial velocity of 300, and it says it stops in 2 seconds, so V final is 0, and I'm asking what's the acceleration. Okay, and that reminds you of equation 1. Okay, but now we're doing this in the rotational world. All right, okay, so I have a CD spinning at 300 revolutions per minute. Okay, so they still sell CDs, and some people still use CDs, so I want to skip 1 page. I'm going to come back to this. Okay, so I want to look at a 12-inch vinyl record versus a compact disc. Okay, these are not to scale. Remember, the CD is smaller than the record. Okay, so what's the difference between how these things work? All right, so we showed that when you use the record, okay, the vinyl record, that it spins at a constant rate. Okay, so omega is constant. Okay, so the omega is 33 1/3 revolutions per minute. Okay, it's not in the correct units, right? It has to be in radians per time. This is revolutions per minute, but this represents the rotation rate. Okay, it doesn't matter whether you're playing the first song. Okay, so the first song is on the outer part of the record, last song is on the inner part. It always spins at a constant rate. Okay, if you look at a vinyl record, you can see the wiggles more in here, and here the wiggles are all compressed. Okay, that's why it always sounds better out here, and it sounds crappy there. All right, because the what do you call it? The wiggles in the vinyl, the little waves made in the vinyl, the grooves are so close together you don't get the same sound as when they're wider apart. Okay, with the CD, okay, biggest difference with the CD is that the spin rate is not constant. It actually depends which song you're playing on the CD. Okay, and the CD, okay, the first song is on the inner track, last song is toward the outer. Okay, and the spin rate of a CD varies from about 200 revolutions per minute to 500. Okay, so the record is 33 1/3. This thing goes from 200 to 500 RPM. And the reason is, again, this is an audio CD. Okay, it's not a data CD that you burn your data to a DVD or something like that. Okay, so for an audio CD, okay, here's your little laser head. The laser likes to read a certain amount of data at the same time. So for example, let's say this length here, that length, okay, on the CD, that purple length, okay, let's say this strip, okay, that length of strip, all right, represents 1 second of music. Okay, so this is 1 second of music, all right. So for the audio CD, this strip, okay, that strip of data has to pass by that laser head in 1 second. So the laser wants to read a certain amount of data, okay, which is 1 second of music, okay, at a constant rate. So on the inner song, okay, so for the inner song, this strip of data, that length of data, okay, if it starts here, goes almost all the way around. But for the last song out here, that strip of data only takes up about a quarter way around. It's about 90 degrees. Okay, so remember, the angular speed is the change in angular displacement, okay, or that delta theta per time. Okay, Now, let's say for the first song, the inner song, that's over here, okay? To play the first song, or to play 1 second, let's say this is 1 second, to play 1 second of music, this thing has to rotate, because that purple strip of data, okay, that purple strip of data, for the inner song, goes almost all the way around. So that's a huge angular displacement, okay? But for the last song, okay, the outer song, this same strip of data, okay, only takes up about a quarter of a rotation, or about 90 degrees. So that delta theta is small, right? That's only about 90 degrees. So for the disc to play 1 second of music from the first song, it has to go almost all the way around, okay? But to play 1 second of the last song on the outer part of the disc, it only has to go about a quarter of the way around. So it has to rotate really fast, okay, for the inner song, because it has to take that 1 second of music and rotate almost all the way around, okay? So that's why the inner part of the CD, okay, the first track is going about 500 revolutions per minute. The outer track doesn't rotate as fast. It's only going about 200. Okay, so go back here. Okay, so that's why I just said this is some intermediate track. It's going at 300 revolutions per minute, okay? So essentially, this is my omega initial, okay? It stops, that's my omega final, and that's my time, okay? And I want to find the angular acceleration, that's delta theta. Oops, no, it's not. My angular acceleration, that's my angular acceleration alpha, okay? So here's the pattern. I have omega initial, omega final, and a time. So that reminds you of equation number 1, okay? Okay, so omega final 0, because it stopped. I know omega initial, that's my 300, but it's not in the correct units, okay? So this has to be in radians per second. So I took my omega initial, I said in one revolution, I have 2 pi radians, and in 1 minute, I have 60 seconds. So the minutes canceled, revolutions canceled. Okay, so that's my correct units of omega initial, all right? I solved this algebraically for alpha, and I put in omega initial, okay, put in my omega initial is 10 pi, okay, radians per second. There's my time, and there's my angular acceleration. Now, what does it mean that's negative? Well, same for the car, right? When this thing's slowing down, velocity is to the right, acceleration points backwards, the acceleration is negative. So here, the angular acceleration should be negative because the disk is slowing down to rest, okay? Part 2, what's the total angular displacement? Okay, that's delta theta. So number 2, back in chapter 2, would be how far did the car go? Okay, you're looking for delta x back in chapter 2, all right? So I want to know the total angular displacement delta theta, all right? Meaning how many times did it rotate, but in the units I want, all right? So that's equation number 2, all right? So I have my initial angular speed, okay? That's my, that's my 300, okay? But remember, I had to convert it to the correct units. There's my omega initial, okay? There's the time it takes to stop. There's my angular acceleration. Remember, it's putting on the brakes, it's slowing down. Like when you slam on your brakes of your car, your wheels slow down, the rotation rate. And there's my alpha. Okay, so those S's cancel, and I wind up with 10 pi radians. Okay, so that's my angular displacement while this thing is coming to a stop. Now, I could have used equation number 3, okay, because omega final 0, I know omega initial is a number, and I know alpha is a number. So I solved this for delta theta, okay, put in my omega initial, and I wind up with the same thing. So we saw back in chapter 2 that there's usually more than one way to solve some of these problems, okay? So this is what I was asking to find. That's my angular displacement, okay? Now we could ask, how many times does it rotate, okay? Well, if that's my angular displacement, I'm going to change radians to rotations. So I said in 2 pi radians, I have 1 revolution. Radians cancel. So that things that rotate it 5 times before it stopped. This section deals with the concept of center of mass and system of particles. Okay, so it's a little deviation of what we've done in the past, but we're going to relate it to what we've done with momentum in this chapter and Newton's second law from previous chapters, and also energy eventually. Okay, so they talk about a system of particles. So let's say I have a meter stick here, okay, and we want to find what's called the center of mass. So what I did is I showed, here's my meter stick. So for all practical purposes, think of the center of mass is where you would put your finger to balance it, okay? Now, obviously, if you're out in space, okay, you can put your finger anywhere because everything is weightless, okay? That would be talking about a center of gravity, which we'll do in the torque chapter, but for practical purposes, just think of where you would put your finger to balance this thing. And so I'm going to use this symbol to represent, that's the location of the center of mass. So it's a geometric point. So what we want to do is we want to show that a body or a system of particles, okay, move as if two things are occurring. Okay, we want to show that, let's say the meter stick, okay, acts as if the mass was concentrated at one geometric point in space. That geometric point is called the center of mass. And the reason it's called a geometric point is the center of mass doesn't necessarily have to be on the object. Okay, like for example, okay, let's say I had something like this. Okay, put one of those. Okay, like a donut. Okay, center of mass, okay, is in the middle. Okay, it's not even on the object. Down here, I have a boomerang. Okay, center of mass isn't even on the object. Okay, so it's a geometric point. All right, so we want to show that a body or a system of particles move as if two things, that all the mass is concentrated at that one point called the center of mass, and that the body acts as if the net external force was applied at that point. Okay, now what I mean by that is let's say I have a meter stick up here, okay, and let's say you balance the meter stick on your finger, and let's say the meter stick has a mass of 100 grams, okay, so there's your finger, okay, you're balancing it on the meter, or you're balancing the meter stick on your finger, and the meter stick has a mass of 100 grams. Well, what if instead you just had one of those 100-gram masses from our lab, okay, and it was dark and your eyes were closed, all right? You couldn't tell whether you had the meter stick at the tip of your finger or that little round cylindrical mass on the tip of your finger, okay? Why? Because they have the same mass, all right? So we want to show that when your finger is balancing that, okay, that the net external force, okay, so here you have mg, here you have mg, okay? The net force seems to be acting at that geometric point called the center of mass, right? Okay, now, they talk about a system of particles. Well, let's say I have an object like this. How many particles make up this system, okay? Right, if I took this whole baseball apart, okay, and I counted how many particles would there be? Well, from chemistry class, right, it's on the order of 10 to the 23rd, right? Avogadro's number of particles, all right? So instead of having to draw for our meter stick, there's an mg for that little particle and mg for that little particle, okay? Instead of drawing 10 to the 23rd little mg's up here, okay, this stick acts as if there's one mg that acts at the center of mass. So that's the motivation for looking at the center of mass of a system of particles. Okay, so let's say I have two particles. These could be like two tennis balls or something, okay? And this is the road. Just think of this as the road. Okay, so the road is my x-axis. And this is my origin, okay? This is x equals 0. And one is at the 2-foot mark and one is at the 4-foot mark. Okay, I'm using feet because I didn't want to use m for mass and m for meters. Okay, so I have a tennis ball at the 2 feet mark, tennis ball at the 4-foot mark. Okay, so if I want to find the coordinate of the center of mass, this is the location of the center of mass. Okay, how I do that is I go out to the location of each one. Okay, x1 is the coordinate, okay, of number 1, okay, and I multiply it by the mass of number 1. And then I go to the coordinate, the location of mass number 2, and I multiply by the mass of number 2. okay? But that would give me mass times a distance, and I'm looking for a location, okay? So I divide by the sum of the masses. And so I have mass units on the top, mass units on the bottom. So the mass units would cancel, and that would give me units of distance, okay? So we haven't derived this, okay? Haven't derived that. Okay, we'll do that when we get to the chapter on torque, right? So we're just gonna see if it works in a special case for, let's say I have the 2 tennis balls, okay? So what this is, okay, this position of the center of mass, this gives us the average position of the particles weighted by their mass, okay? And I'm using the word weight like a statistical weight. It's a weighted average, right? So it would make sense that if this was my M1 and that was my M2, that the center of mass would be much closer to number 2, okay? And what I mean by that is, imagine if you had a stick between these two, okay, and you wanted to balance these two on your finger, okay? Your finger would probably be more over here toward the big one, okay? Kind of like a dumbbell with a big weight on one side, a small weight on the other side, okay? So this would give us the average position of the particles weighted by their mass. Where, let's say this is the moon, okay? As an example, that's the Earth, okay? And you can actually calculate the center of mass of the Moon-Earth system, and actually the center of mass of the Moon-Earth system, okay? If you could connect the moon and the Earth by a bar and put your finger there and balance it, okay? It's actually somewhere over there, somewhere in the Earth, okay? So in that case, the center of mass of the system is within M2, okay? So back to the tennis ball problems, all right? So this gives us our average position, okay? Again, I didn't derive it. We just threw it out there. But to see if it works, let's see if it gives us our expected answer where the masses up here are the same, all right? Because if the masses are the same, then the center mass should be in the middle, right? And let's see that. So if masses are the same, okay, I'm going to use this expression here, okay? So I go out to the coordinate of number 1, which is at 2 feet, multiply by its mass, and then I go to the coordinate of number 2, that's 4 feet, okay, multiply by its mass, and then I divide by the total mass, m plus m, all right? So on the numerator, I have m2 feet, right? So you can see why I'm not using m for mass and m for meters. So I have m2 feet plus m4 feet gives me m6 feet, and the bottom I have m plus m, which is 2m, so the m cancels out, okay? M is mass, the m cancels out, and I get 3 feet, okay? And that's what you expect, right? So if these 2 tennis balls are the same mass, then the center of mass should be between them. Meaning if you connected these 2 with a stick, okay, you could put your finger right there and you can balance them, all right? So just think for now as the location of where you could balance these, all right? So again, we didn't derive this expression, we just tested it to see if it gives us the expected result in the limit where we have 2 masses and the masses are the same, okay? Okay, so we just had this, that was for 2 masses, okay? Now we're gonna do it for 3, 4, and n masses. So we just did that, okay? Now I'm gonna extend it to 3 of them, 4 of them, and out to n. So essentially, if I want to find the x-coordinate center mass, I go to the coordinate of each object, multiply by the mass of that object. Go to the next coordinate, next object, its coordinate, okay? But I have to multiply by the mass, okay? And then I divide by the sum of the masses. That gives me my weighted average, okay? So I can write the numerator like that, and I can write the denominator like that, okay? So this is a compact way to write the x-coordinate, the center of mass, right? And you can see, whoa, right, that unit-wise, that would have kilograms, and those kilograms would cancel, and you're left with units of meters, okay? So dimensionally, it's okay. All right, and then if we had a 2-dimensional problem, instead of the tennis balls like this, maybe one was up here, one was down there, and you want to find the y-coordinate in the center of mass, it looks the exact same as that, Okay, now you're doing the y coordinate. And you can also generalize it into the z coordinate of the center of mass. It would look the exact same. Another way you can find an object center of mass, okay, maybe you have some object with a weird shape, okay, let's say two-dimensional, okay, and you want to find the coordinate or the location of the center of mass. You can actually hang it from a string, okay, and I'll show you a video that does that exact same thing.
In this demonstration, we're going to see how to find the center of mass of an irregularly shaped object. For the object, we're going to use the state of North Carolina. So I'll begin by putting the pin here. This can be anywhere, but I'm just picking somewhere around Elizabeth City. I hold the end of the pin so that the map is suspended from my hand. So this means that the center of mass of the map will be somewhere along this vertical line. With a marker, I'll draw the line on there. It's kind of a rough line, but you get the idea. So we know the center of mass falls somewhere on that line, but we don't know where. In order to find out, we need to draw a second line to intersect with the first. So to do that, I'll put the pin in somewhere else, somewhere up here around Boone. Suspend it once more. Draw another line. And that's enough to find the center of mass, which should be the intersection of those two. But just for good measure, we'll do it one more time to see if the third line also passes through that point. So I'll put this somewhere down around Wilmington. And I don't have to draw the line for you to see that the string is passing very near that intersection point. So no matter where I put that pin, it should pass through that particular point. And let's see where that is. It turns out that it's very close to the city of Sanford. So if that really is the center of mass of North Carolina, then I should be able to balance the entire state on that particular point. Now, when I said that Sanford was the center of mass of the state of North Carolina, I was talking about this cutout of the state.
Okay, so not only did we want to show that an object has this concept of the center of mass, that location, okay, but we want to show that an object moves as if the net force is applied at that location, the center of mass. So I'm going to show you a video where I have, let's say, something's moving, okay, like this hammer, and if I looked at maybe one spot of the hammer, maybe the tip, okay, that would follow a very complicated path. But if I choose to look at the center of mass, which is this dot here, right there, that dot right there, okay, or how about that dot there, okay, that dot, okay, which is the center of mass, acts just like our projectile. So that dot just follows a parabolic path because the only force that's acting on the object, okay, is its weight, and that weight appears to act at the center of mass. So we want to show that the center of mass of the moving body, okay, acts as if the net force is applied at that point. So I'll show you that video. Okay, so here's a top view. I have a ruler on a table. Okay, on an air table, like an air hockey table. Okay, so if I give the ruler a quick push, okay, which is an impulse, okay, so my finger is going to exert an impulse, okay, so a force acting over a short period of time. So while my finger is in contact, while the force is in contact, Newton's second law says that if the force is to the right, my finger force is to the right, the center of mass is going to accelerate to the right. So that while my finger is touching it, the center of mass starts to accelerate to the right. Now my finger is no longer touching it, so there's no more acceleration. So the center of mass keeps moving to the right with constant velocity. Okay, but if I exert my force up here, okay, all right, still using this, while my finger is touching it, okay, while I'm exerting a force to the right, the center of mass starts to accelerate to the right. Now my finger is gone. My finger is not touching it, is only touching it for a short period of time. So that means if there's no external force, or no net external force, that the center of mass can't accelerate. So the center of mass moves at constant velocity to the right. Okay, but the rest of the stick keeps rotating. Okay, so the center of mass moves at constant velocity in a straight line. Okay, while the rest of the object rotates. So I'm actually going to show you a video on that where I have an irregular shaped object. Center of mass is over here. You exert a force on it, and that center of mass is going to move in a straight line while the rest of the object, okay, keeps rotating. Okay, so we just looked at the concept of center of mass, all right? Because in these chapters, we're going to be inventorying or looking at things regarding what's the motion of their center of mass, all right? Because when a wheel rolls down, or when a car wheel goes by, if you look at a point on the rubber tire, okay, or where the lug nut is, okay, that's a much more complicated path than just looking at the exact center of the axis of rotation along the axle. Okay, so I want to look at the concept of rolling. All right, so let's look at a stationary wheel rotating with some angular speed. So let's say you take off your bike wheel, okay? You're holding it with your hand. Okay, there's your hand, all right? Let me take the hand away. Okay, and I'm using this little symbol right there, okay? This symbol represents an axis of rotation. Okay, so I make a little triangle with a dot. That means this thing is rotating about that axis, all right? Okay, so this thing is just purely rotating. You're holding the axle, and you gave this thing a spin, and it's rotating. So I just drew the velocity at different points of the rim. So the top of the rim is headed to the right, that part's headed down, that's headed to the left, that part of the rim is headed up. Okay. Now we know previously that the linear speed of any part, okay, depends on how far you're out from the axis of rotation. So V is R omega. Okay, remember, every part of the wheel has the same omega. Okay, because remember, omega is delta theta per time. So if I take, we did this point before was A and that was B, okay, right? Both point A and point B both go the same delta theta, right, 2 pi radians, in the same time. Okay, so that's why there isn't an omega for A and omega for B, okay? There's just one omega for the entire wheel. There, let me get rid of that too. Okay, so this wheel is purely rotating, and I just drew the directions of the linear velocities v at different points of the wheel. Okay. Now, I'm going to take the same wheel and I'm going to have it roll along the ground without slipping. All right. And I'm going to show you a video in a second what's going on here. Okay, so this is the bike wheel, and it's going to rotate with the same angular speed as in this picture. Okay, so let's say I gave this thing a spin with my hand, okay, and it's rotating around, and whatever the spin rate, I'm now going to roll it on the floor with the exact same spin rate. Okay, now I said up here it's going to roll without slipping. All right, so if you're in your car and you slam your foot on the gas pedal, okay, your tire is going to spin really fast, okay, and your car is not going to go very far, and then eventually the tire is going to slow down due to friction, and then it'll grip the road, and then it's going to start to move. All right, so I'll show you a video of a bowling ball that is thrown, and when it hits the ground, it's rotating really fast. Okay, it's slipping, and then it eventually grips, and then it starts to roll without slipping. Okay, so that's what it means to roll without slipping. Okay, and then I'm not going to keep saying the phrase without slipping. I'm just going to say something rolls. Okay, so something's rolling, it means it's not slipping. Okay, so I have the wheel. Okay, so what it is I drew, here's the center of mass. Okay, so remember previously, if I make a little X with a circle, okay, that's the center of mass. There's my center of mass. All right, and this thing is moving to the right. And let's say the center of mass goes from that point on the road to that point on the road. Okay, so I'm not calling this the x-axis, I'm calling it the s-axis. Okay, now why am I using the letter s? Okay, we'll see. So this is the distance s that the center of mass moves. And there's some paint on the ground. All right, and as the tire rolls over the paint, okay, that paint, winds up along the edge of the tire, okay, along the rim of the tire. So this distance s is the same as that arc length s. Okay, and I said in geometry class and trig classes, they like to use s for arc length. So if that's an arc length s, I'm going to call the path along the road s. That's why I call that the s-axis. Okay. Okay, so the speed of the center of mass. Okay, so remember speed. Okay, speed is distance over time. So the speed of the center of mass. Okay, speed of the center of mass is the distance. Okay, I could have called it s. I just called it delta s. Okay, so that's my distance, delta s or s, divided by the time. Okay, now we know from earlier when we had a sector of a circle, that was arc length and that was the radius, that was theta, that the arc length s is related to the radius and theta like that. So s is r theta. So right here I have an s, I put in r theta. Okay, now the radius of the wheel is constant, so that comes outside. Okay, that's outside. And delta theta per time, that's the angular velocity omega. So that says V center of mass is r omega. And that's the condition for rolling. Okay, so the condition for rolling is that as long as the speed of the center of mass, right, is r omega, that means it's not slipping. Okay, so let me go back again. So here I have a wheel rotating with some angular speed omega. Okay, now I have that same wheel, okay, rolling with the same omega. Okay, and if that's happening, then that condition is met, that the speed of the center of mass is r omega. Okay, here I have V center of mass is r omega. If I divide it both sides by delta t, okay, velocity per time is acceleration, and on the right, omega per time is angular acceleration. So that's where this came from. Okay, so this condition for rolling, V center of mass is r omega, also says that the center of mass, or the acceleration center of mass is r alpha.